Okay, before I start, are there any questions? From could be before the break, could be about the JFET thing that we talked about last day. Could even be about the videos that were uploaded today, but I'm not very sure most of you have seen that yet. So are there any questions?
Sir,
Yeah, go ahead.
sir, I did not understand how the potential divider tricks the transistor like into thinking there are two batteries.
Well, the look, the basic idea was simply this. You have a circuit which goes like this. Okay, pardon my rather bad drawing, but so this is the RC, this is the RE, and we did not have the potential divider. You would have a resistance RB here. Now, let's make one thing very clear. Suppose I had a battery VCC, another battery VBB. VBB is a base bias battery. Then we can actually work perfectly well with this particular setup because remember the basic job here is this. RE has to be large enough to provide enough negative feedback so that the circuit behaves stably. That is the suppose for any reason beta changes or for any reason temperature changes, the circuit does not drift too much because any say increase in this current would also increase this current. So the moment this current goes up, the emitter goes up, and that makes the base emitter voltage go down. And if the base emitter voltage goes down, that pulls the current down. In other words, any attempt for the current to rise will produce an opposing effect, which will make the current come down again. It will not come down to its original value or even go below that, but it will not rise as much as it should have. That's the basic idea behind this RE. So this is a stabilizing thing. Now the only real problem is when you want to bias this, you have to remember that this is a base, this is a collector. So the base collector junction has to be reverse biased. Now if we have drawn an NPN transistor here, and that means if you want the base collector junction to be reverse biased, you want the collector to be bigger than the voltage at the base, right? Is that clear?
Yes, sir.
Now, if, for example, we had used the same battery, you had just used one of them here, then in order that VC be bigger than VB, you would want a larger drop across RB. Because they're both starting at the same point, right? So if you want this end to be smaller than this voltage, then you would want drop across RB to be bigger than drop across RC. But the whole point in the stabilization is when you look at this particular loop, you have a drop across RB, you have a drop across RE, and you have a VBE drop. Basically, stabilization occurs because drop across RE dominates. Okay. Now, if that happens, so the problem is you want drop across RE to be bigger, much bigger than the drop across RB. On the other hand, in order to ensure a reverse bias, so that in order to ensure the transistor does not go into saturation, you would want the drop across RB to be even bigger than the drop across RC. That would end up giving a very tiny drop across RC, which you can achieve by using a very small resistance there. But the trouble is, any current fluctuation that occurs here that causes a current fluctuation in IC, and that multiplied by the resistance essentially gives you the voltage drop. So the voltage output voltage signal will become very tiny if you're forced to use a very small RC. The problem with this circuit is that although you have stabilization, in order to get good stabilization, drop here has to dominate over the drop here. At least be 10 times more, if not 100 times more. That, of course, means this has to be a rather small drop. But because you want active region, drop across RC has to be even smaller. Remember, RC carries a current which is 100 times bigger, or of that order 100 or more, compared to RB, right? So despite that, if you want the drop across RC to be small, you would need a tiny value for the resistance RC. That would also mean that any voltage gain that you could get, output voltage signal, would also be tiny. So this circuit is really not very useful. It goes into saturation very easily, or the only other way to make it not go into saturation easily is to essentially have a very, very small RC and hence a very small gain. So the trick that is, of course, the thing that you could do is simply use another voltage source. If VBB is smaller than VCC to begin with, say half of VCC, then you can safely put in reasonable resistances here. Even if this drop is much bigger than this one, it's still not going to go into saturation, simply because you have already started lower. So even with a small drop, you are also going to still end up lower. Okay. Of course, there's a limit to how small it can be, but it can at least be achieved much more easily. Now, the question that you are asking is not that. The question is, this is fine. If you use two different voltages, saturation will not occur. That's pretty easy to understand. If you use a smaller VB, but what you use actually is not two different voltage sources, but you use something like this. The class actually for it. So this is what is called the potential divider arrangement. Okay. So your question was, how does this help? Is that what you're asking?
I think yeah, like I think in your lectures you said like it tricks the transistor.
Yeah,
I think.
the tricks is just a way of speech, but basically what happens here is this. There are two ways of understanding this. You can actually analyze this circuit using Kirchhoff's laws, or the easier way to do would be that because you want to analyze what's happening in the out here at the base, you just think of this. Okay, my drawing skills are really rather bad, but let's see. Let's say you can think of this as something which is inside a black box. Okay, with this terminal sticking out, and of course the ground terminal sticking out. Okay. So inside the black box, you have VCC, you have R1, you have R2, and with this pair of terminals sticking out. So if you have one pair of terminals sticking out of a black box, what's the obvious thing that you could use? Thevenin's theorem, right? Is that okay?
Yes, sir.
And then you can just replace this black box by its Thevenin equivalent. Now, what is the Thevenin equivalent here? That's straightforward, because if you want to find the Thevenin voltage, you have to open out this, right? That means you have to just disconnect the transistor. Just think of what is the voltage between these two ends when nothing is connected to it. Now, when nothing is connected here, this is just a series circuit with R1 and R2. So how much is the voltage across these two terminals? Remember, we are saying this whole thing has been disconnected. You just have VCC, R1, R2, and this pair of terminals sticking out. And that pair of terminals is now open because you want to calculate the Thevenin voltage. So how much is the voltage across that pair of terminals?
R2 VCC by R1 plus R2.
Right. It's just series potential division. R2 and R1 are two resistances. So what you're going to get is R2 by R1 plus R2 VCC. That's the Thevenin voltage here. And the Thevenin resistance, well, there are many ways of finding out. You can short this out and find out. If you short this out, of course, how much will the short circuit current be if I just put a short here? If I put a short here, how much will the current be? The voltage here is VCC. This is R1. Now you have R2 in parallel with the short. If R2 is in parallel with the short, how much current will flow through the short? Forget the transistor, forget RC, forget RE. All these have been disconnected. You just have put a short here.
Is it VCC by R1?
Exactly. Because R2 in parallel with a short is just a short, right? And all the current goes to the short. Now, there is no current division here. Whatever current comes in here goes to the short. And so it's just VCC by R1. That's the current. So that's your ISC. If you divide VThevenin by VOC by ISC, you're going to get the Thevenin resistance. Or you could just say, okay, let's look in from this end by making the input voltage 0. Now, if you make VCC 0, that means you're basically connecting this point to the ground, right? Making a voltage 0 is the same as connecting the point to the ground. That essentially means that this R2, which is between this point and the ground, is joined by R1, which is also between this point. It was between R1 and VCC, but now that you have made VCC equal to 0, you're going to get R1 also. R1 in parallel with R2. So either way, you get R Thevenin is R1 parallel to R2. So what happens? What happens is this. You had this circuit, RC, RE, R1, R2. But if you replace this part by a Thevenin equivalent, what you still get is VCC, RC. This part, of course, VCC still is there on this part because it's biasing the RC and through it the transistor on this side. But you have replaced this thing by its Thevenin equivalent, which essentially means that this is now R1 parallel R2 and VThevenin, which is so that's the trick. Basically, now it looks like Thevenin's theorem essentially is the trick. The trick essentially is that now it looks like the base is connected to a smaller voltage. Remember, we said if instead of VCC, you had a VBB here, which is smaller than VCC, you would be able to avoid saturation and not be forced to use a very small value of RC. You get the point now. What we have essentially done is the potential divider via Thevenin's theorem effectively behaves like it is producing a smaller voltage R2 by R1 plus R2 VCC. So it's effectively behaving like a smaller bias battery. Why is this better than using a smaller bias battery actually? The answer is bias batteries cost money. They cost a huge amount of money, by the way. Batteries would be the most expensive component in this circuit. Okay, so you can cut down from 2 batteries to 1, you have actually essentially halved the cost, almost. Because compared to the battery, everything else costs very little. Is that okay now?
Yes, sir.
Okay, so you have to realize that behind this circuit design, there's a lot of thought which goes in. That is, you start with just a simple fixed bias, then you realize that fixed bias has problems. That is, fixed bias directly fixes IB. So whenever there's a temperature fluctuation, CEO can drive the IC to unacceptable values. If the beta changes because your transistor has grown old, or simply because you have to change your transistor, or simply because the temperature has changed and beta does change drastically with temperature, then your IC will change drastically. So that is why you need a stabilizing effect. That's why you put in a RE. But just to remind you once again, the equation here is VCC minus, if I just use this circuit, minus, and call this IB, RB. So IB, RB, oops, what happened? Oh, somehow I killed my file. Let's try restoring it. Yeah. So if you wrote VCC minus IBRB minus, not VCC, sorry, Thevenin. RB is of course R Thevenin. So you can either call this V Thevenin or can pretend that you are using a different battery and call it VBB. Minus VBE minus IERE equal to 0. So this is the equation. Now the important thing to realize here is if you were using comparable values of RB and RE, then IERE would dominate a lot over IBRB. So approximately IE will be given by VBB, sorry, VBB minus VBE by RE. Now that's not exact, but if this usually typically this term will be much bigger than this, so that's what you're going to get. So IE is now being fixed by the circuit. Of course, if IE is nearly fixed, then IC is also nearly fixed. Right? In a fixed bias circuit, IB is fixed. Now, if IB is fixed by your circuit, then variations in beta, variations in temperature can have a huge effect on IC and hence on VCE. So your bias point is going to drift like anything. Here on the other end, in this circuit, what is being fixed essentially is IE, and IC is alpha times IE. Even if beta changes a lot, alpha changes only a little bit, right? Because say beta going from 10 to 100 would have actually multiplied the IC by a factor of 10 in a fixed bias circuit. Here on the other hand, if IE is fixed, IC is essentially alpha IE, and beta is 10 means alpha is around 0.9, and beta is 100 means alpha is 0.99. So it is going to change, but it's going to change a lot less. It's going to change only, say, 0.09 out of 0.9, so only 10% compared to when this happened, when IB were fixed, then beta going from 10 to 100 would mean IC would change tenfold. Here it would change only by 10%. So beta fluctuating from 10 to 100 is very unlikely. I'm just using it as a rather extreme example. But whereas for a fixed bias circuit, IC would change a huge amount. For a circuit in which IE is more or less fixed by the circuit, that would have to sort of rely on that would have to sort of rely on the fact that alpha changes a lot less than beta changes, than when beta changes. And one important point has to be borne in mind that this IE being fixed works only because you can ignore IBRB compared to IERE. So that is why I said if you want good stabilization, the drop across RB has to be very, very small compared to the drop across RE. And the drop across RC has to be even smaller in order to achieve active region if you are using the same supply, unless you are using potential divider to make one supply look like two supplies. Basically, that is really the trick, right? The VCC here looks like you have a VCC, also looks like you have a VThevenin. So it looks like you have two different voltage sources, but you actually have only one. So the cost of one, but the utility of two. Okay? Any other questions? Okay, if not, then what I'm going to do is I'm going to discuss op-amps today. Just op-amps are there in the video, so those are the ones you are supposed to see. I'm just going to give you a quick introduction to them so that it makes it easier for you to watch the videos, although all that I'm going to say is really there in the videos as well. On Mondays, we will start with, we talk about JFETs again, JFET circuits. Okay. In the Monday class, we will talk about JFET circuits again. Okay. So op amps. This of course is a short abbreviated name. They are actually formally called operational amplifiers. And the name operational actually stands for mathematical operations. The reason why op amps were used originally, and one of the major reasons why they are still used today, is in actually implementing mathematical operations. That's why the name operational amplifiers came into being, or op amps for short. Okay. So what are they really? They are a bunch of things called differential amplifiers. So basically, the way this differs from the amplifier that we talked about for transistors is this. Let's call them V plus and V minus. So unlike ordinary amplifiers, which have one input and one output, differential amplifiers have two inputs. And we are calling the inputs V plus and V minus. Okay, voltages at the two inputs are being called V plus and V minus. So what it does, it amplifies not V plus or V minus, but amplifies the difference in the two voltages. Okay. Now for op amps, something else is important. It's not just a differential amplifier which amplifies the difference between the two voltages. It's characterized by what you would call near ideal. So it's or almost ideal amplifiers. So this is a voltage to voltage amplifier, right? It takes in a voltage, puts out a output is also a voltage. The voltage that it amplifies is the difference of the two voltages, but still a voltage. Now, we have already talked about that in the context of transistor amplifiers. If you have listened to the videos, you would have definitely listened to that. Question I'm asking you is, what are the characteristics of a very good amplifier? What would you want it to have? So we have already talked about several characteristics that an amplifier can have. The most obvious one is the gain. Then you have input impedance, output impedance, you also have other parameters like the bandwidth. There's a frequency range over which the gain is more or less stable, and so on. So ideally, what would you expect a very good amplifier? If it's a voltage to voltage amplifier, what property should it have? About what should the gain be like? If you can imagine the best possible amplifier, what kind of gain would you want it to have? Come on. Tell me, if you were to build an amplifier and wanted to call it a very, very good amplifier, what kind of gain would you want it to have? Low gain, high gain, no gain at all? High gain, right? Okay, this is a bit of a trick question, but I'm going to refute that soon. But anyway, high, ideally infinite. Now, an actual op amp does not really have infinite gain, but it really does have a very high gain. Here, gain for an op amp means the differential gain, that is the ratio between the output voltage and VD. And that's safely 10,000 or more, in that way more than 10,000 usually. 10,000 is pretty conservative for an op amp gain. A decent op amp has gains of the order 20,000 to a million. So that's what an op amp's gain is like. Okay, what about input impedance? Would you want an op amp, would I want a good amplifier, good voltage to voltage amplifier to have a high input impedance or a low input impedance? Remember, as far as the amplifier is concerned, to the source, which is essentially a voltage source with a series resistance, the amplifier looks like a impedance, Zi. The question is, do I want a big Zi or a small Zi?
A big Zi.
Why?
Heating.
So that more of the voltage falls across the Zi.
Why? Good, but why? Of course, here if you have this circuit, it's pretty easy to see that the voltage which goes across Zi, which is also the voltage which is actually input to the amplifier, V in, is actually Zi by Zi plus Rs Vs, right? So now the question is, bigger Zi will make V in bigger. That's pretty obvious. But why would you want that? Come on, that's a pretty straightforward and easy question. Why would you want the input to the amplifier to be large?
For the output to be large.
Good. Okay, that could be a good first starting point. After all, an amplifier can only amplify what it gets. The amplifier doesn't care how much Vs is, the source voltage. The amplifier does not amplify the source voltage. The amplifier only amplifies the voltage that it gets. So if Vin is larger, then of course it's going to amplify the larger voltage and produce a larger output. Okay. So if you use a small Zi, you're going to get a smaller output. If you use a large Zi, you're going to get a larger output. As simple as that. But is that the reason why you want this? To get a big output? I've actually said this several times in many of these videos. A good circuit design is not necessarily one which gives you a big output. You may not want a big output always. Sometimes you may even want a small output. What is a good design? For an amplifier, of course, your aim is ultimately to produce an output voltage. But it may not always be to produce a big output voltage. But it's much more important to produce a stable output voltage. Notice that the input voltage here, the voltage which actually gets amplified, depends on Rs. Not only Vs, it also depends on Rs, right? The source resistance. If Zi is very big, then much bigger than Rs, then this factor here in front of the Vs is almost equal to 1, right? In that case, it does not matter how big Rs is. In other words, your amplifier will work equally well with a 10 ohm impedance source or a 50 ohm impedance source or a 100 ohm impedance source. On the other hand, if your Zi is much bigger than say 100 ohms, but if Zi were 100 ohms, then if your source were 10 ohm impedance, then you would get 100 by 110 of Vs, almost all of Vs. But when your source impedance is 100 ohms, you will get only half of Vs. It's not as if that we are not really that worried that the gain is going down. We are more worried that if you change your source, the behavior of your circuit is going to change. A gain which may be acceptable for a low impedance source, if you change it to a high impedance source, you may end up with too small a gain for the circuit to work. That is where the problem really lies, not in the largeness or smallness of the output, but in the fact that the output here would depend strongly on external parameters, which is why for a good circuit, for a good amplifier circuit, a high input impedance is essential. If you have a high input impedance, it doesn't really matter what kind of a impedance source you're connecting to it. Okay, so that is the real reason, not because you want a huge gain, but simply because you want a gain which is stable against variations of the input circuit components. And you do want a high input impedance. And for op amps, again, it's very nearly ideal to get around 1 mega ohm or more. Okay, output impedance. Output impedance is that the output essentially looks like V in times AV. For the op amp, it will essentially be a gain, this gain, times VG, the differential voltage, in series with the ZO. Now, would you want a big ZO or a small ZO? Remember, this is not the output. The output is you connect an RL here and get the voltage across the RL. So would you want a small ZO or a big ZO?
Small Z.
A small zero.
Yeah, and again, the reason is not because small ZO will give you a big gain. It will, but the important thing is small ZO will mean that whether RL is a kilo ohm or 10 kilo ohms doesn't matter if ZO is say a few ohms. You understand that? The output is going to be RL by ZO plus RL times AVVN. Just a series potential division once again. And so if ZO is tiny compared to RL, then this result is almost, ratio is almost 1 and you're going to get AVVN. That means as long as RL is much smaller than ZO, it will not matter whether RL is 1 kilo ohm or 10 kilo ohms or 100 kilo ohms, as long as ZO is much smaller than RL. Okay? And RL once again is external to your amplifier. So having a small ZO essentially ensures that your circuit is independent of the external connections that you have to make. And small actually, okay, what is a small resistance, by the way? When you say small resistance, what kind of resistance do you mean? Milliohms, microohms, what? What is a small resistance in an electronic circuit? What is the typical resistance in an electronic circuit, as I said before?
Kilo.
Sorry, I couldn't hear you. Just repeat that.
Kilo.
Kilo ohm is a typical resistance. Few hundred ohms. On the smaller side, but still typical. Small resistance would mean a few ohms. And that's exactly what an op amp has. An op amp has an output impedance which is of the order of a few ohms, an input impedance which is order of mega ohm or more, a gain of 10,000 plus. Now, can you see a contradiction between what I said about these wonderful parameters? In these 3 points, this should be you should have spotted that there is a contradiction between what I said is desirable and what we are claiming. I'm not saying it goes against, but I'm saying that I just now said something is not necessarily very good, yet I'm claiming that to be a very good feature of the op amp. Can you spot that?
Stability.
Sorry, could you just repeat?
The thermal stability.
So thermal stability is something we have not even talked about now. At least I'm talking about these 3 parameters only. Among these 3 parameters, I have claimed one of them is great. The op amp is great on all counts. That's what I'm claiming. But I've also said that one of these points is really not important. Really not the actually important thing, rather.
The gain.
Good, the gain. I just said a while ago that having a huge gain is not really our aim. Our aim should be having a stable gain. Yet I'm claiming that op-amp is such a great circuit because it has a huge, nearly infinite gain. So that should seem a bit contradictory, but actually it's not, because of one thing. You will see that an op-amp, when it's used as an amplifier, is used with something called negative feedback. A negative feedback is essentially a mechanism which reduces the gain. But, and this is very important, it's the negative feedback coupled with a huge raw gain, that is, this is the gain without negative feedback, this huge value. This huge value actually ensures that once you give negative feedback, your circuit has a very, very stable gain, which is what you really want. So having a huge gain is actually good, not by itself, but because you are actually going to use negative feedback to stabilize the gain. And once you do that, once you stabilize the gain using negative feedback, having started with a huge gain is a big advantage. You're going to see that. That's what negative feedback is, one of the major things that we will talk about concerning op-amps, especially when we talk of op-amp amplifiers. The second video that has been uploaded has that. So there you would see that the reason why we are so excited about this huge gain that the op-amp has is that the op-amp, coupled with negative feedback, can give you end up giving you very, very stable gain. So in that sense, it's a wonderful thing to have. Not in itself, not the fact that the gain is 10,000 or more, which is important. Point is, with negative feedback, you can end up getting a gain of 10 rather than a gain of 10,000 or a gain of 100 by tweaking parameter values. But then the gain will then what will happen is, if whether the op-amp's gain is 10,000 or 100,000 will not matter. You will nearly get a gain of 10 if your circuit has been designed to give you a gain of 10. And the reason for that is, again, the gain is so big that it gets lost. You might say, okay, in case you don't understand that, just think of this. Here, this ratio is 1 by 1 plus Rs by Zi, right? If Zi is much bigger than Rs, then it doesn't matter how big Zi really is. All that you can say is Rs by Zi is nearly 0, so this result becomes 1, always. Okay. A very similar thing happens for op-amp gain with negative feedback. It no longer matters whether the op-amp gain is 10,000 or 100,000, you will end up with the same gain for your circuit nonetheless. And that is a very advantageous thing to have. So we will see all that in the actual videos. Those are what this is meant for. But these 3 points have to be borne in mind. Op-amps actually have properties which make them look like near ideal amplifiers. The only difference, of course, is that it's a differential amplifier, not a single input amplifier. But other than that, all the parameters that you want to be high are high. The ones you want to be low are low. Okay. But now, let me just ask you this. This is a typical symbol of an op-amp. Every amplifier actually has this kind of a symbol. The arrow essentially points out that there is an input on this side, and there's an output on this side. That's what this arrowhead is meant to look like. By the way, do you know of any circuit component which has a symbol which looks like this? Other than the amplifier, that is. In your class 12 books, you must have seen a symbol which looks like this. Okay, if you're chatting, what's the chat?
Logic gates.
Which logic gate? Not the AND gate. It's a NOT gate, right? NOT gate is actually, the symbol of the NOT gate is this, right? Where the bubble in front, that's actually the inversion. By the way, strictly speaking, NOT gate symbol really is this. The triangle is added for 2 reasons. One is, if you just put a lot of circles in your circuit, there's every chance that you might get confused and you may miss out 1 or 2. Putting in a big triangle after that sort of focuses the attention on the fact that there's a gate there. Okay, so the job of this triangle essentially is to make the circle visible. But there's a reason why it's a triangle. every gate actually has an amplifier in it. Okay. And so the NOT gate circuit has this triangle simply because a NOT gate has an amplifier. The triangle signifies the amplifier. The bubble signifies the fact that it inverts. Okay. So there also the triangle actually stands for an amplifier. But anyway, let's coming back to the op amp. Op amp symbol is also a triangle, except for the fact that it has two inputs. Okay, when I say two inputs, okay, when I say, for example, when I say two inputs and this is V plus, this is plus, this is minus, a voltage always has to be given between 2 points, right? You can't give a voltage between at one point. That doesn't make sense. A voltage is always a voltage difference. So where is the other point here? When you say you're applying V plus to the plus terminal, you simply can't. You can't give a voltage to one terminal. You have to give a voltage between two terminals. So where is the other one? Similarly, you want to take the output here. But the output also cannot be taken out from one point. It has to be taken out between 2 points. Remember, in the Thevenin's theorem, it's really not one terminal, it's a port. The voltage has to be between two ends. Everywhere the voltage has to be between two ends. The important point to remember is that actually in an op amp, there's a ground connection as well. And all these voltages are given with respect to the ground connection. So when you say this is V plus here, you're actually applying V plus between this point and the ground. V minus between this point and the ground. You take the output between VO and the ground. Okay. Apart from that, there are two very important things which are usually not shown in an op amp circuit, but it's always there, which is the power supply. An op amp has to have a power supply to work. And typical op amps, the kinds that we use, let's say IC741, which is the one which is used most often in a lab, simply because it's a pretty decent op amp, it's also pretty cheap. That has a plus minus 12 volt dual supply. That is, there is one pin where you have to give, an op amp comes in a package with pins. The pins are the connections. And you have to give plus 12 volts to one pin, minus 12 volts to another. Of course, once again, when I say plus 12 volts to one pin, I mean plus 12 volts between that pin and the ground, minus 12 volts between this pin and the ground. Here, this is basically how you set up an op amp. For the op amp to work, you have to have a power supply. The power supply has to be plus 12, minus 12 connected between those 2 points on the ground. You have these two input pins, the ones marked minus and plus, and the voltages there are V minus and V plus, and you get an output V. Okay. Now, when people draw op amp circuits, very often people don't draw the plus minus 12. Not because the plus minus 12 is not there, but because they're always there. They have to be there, otherwise the op amp will not work. So, if you want your op amp to work in an actual experiment, you will have to connect the power supply. Doesn't matter whether your circuit shows it or not. Most circuit diagrams don't show you the power supply because they assume that people understand that amplifiers always need power supplies and that has to be connected. Okay? So basically this is your basic setup. You have two inputs and one output. Now, let me ask you this. Suppose I have an op amp whose gain, as I said, would depend on the particular op amp, but let's say I have an op amp whose gain is 10,000. Sorry, not 10,000 volts, but 10,000. Gain is, of course, just a number. Now, say I've given 1 volt to my minus input and 2 volts to the plus input. Now, how much is the VO? Yes? Remember, VO is gain times VD. So these are the basic equations which op amps should obey.
10,000 volts.
Okay, but do you really believe that?
No.
Good. Getting 10,000 volts out of an op amp this easily would have solved the world's energy problems, but wouldn't work. So something more realistic. How much should the output be?
So
Remember,
around
you have a power
100.
supply. No, don't get. Remember, why are you saying it can't be 10,000 volts? Just because it seems too large. There are plenty of situations where you can produce 10,000 volts, by the way. You would take a sharp needle and electrify it by rubbing it across something. Even with a few strokes, you can easily get more than 10,000 volts at the tip of the needle. Way more than 10,000 volts, by the way. 10,000 volts may be large, but it's not that difficult to come by. But where does the output come from? Or rather, how does an amplifier amplify? Does it produce an output voltage out of the blue? Does it produce an output out of nothing?
So from power supply.
Right, it comes from the power supply. So now, would you
So
modify your
12
answer?
volt. 12 volt.
10 volts.
Close. Okay, I would say 11, 11.5, 11.6, depending on the op amp. 12 volts would be the ideal case that you have a 12 volt supply, you get a 12 volt upper cutoff. But that doesn't really happen. The upper cutoff typically is a bit smaller than the power supply voltage, simply because there are drops inside the op amp. Okay. So basically, this VO equal to AVD, this formula has to be taken with a bit of care. You plot VO versus VD. VO will be AVD. Okay. VO will be AVD, a straight line, up to VO reaching plus saturation voltage Vsat, that's around 12 volts, or on the negative side, minus Vsat, which is around minus 12 volts. In a typical op amp, typical 741, it will be somewhere around plus 11 and minus 11, or plus 11.5, minus 11.5. That depends on how good your op amp is, etc., etc. But roughly, a fixed voltage, let's just say 12 volts for the time being. Let's make it easier on ourselves. So the output will be plus 12 volts, not 10,000 volts. Okay. So now, suppose I change the 2 volts here to 3 volts. What would the output be?
Sir, it would be again same, I guess.
And 4 volts? Five volts, 6 volts. So I change V plus 2, 3, 4, 5, 6. What will the output be?
So output will always be plus Vset and minus Vset.
Which one? Plus Vset or minus Vset?
That will depend on VD. Means,
yeah, but I've told you what V plus is. V minus is 1 volt. Now I'm giving V plus of 2 volts.
Sir, here it will be plus Vset.
Okay.
yes, if VD is positive, then it will plus Vset, and if VD is negative, then it will minus Vset.
So, what is the utility of this circuit, if at all? This is the simplest possible op amp circuit, just the op amp connected to voltages, nothing else.
Sir, this gives stability. If we change the input voltage, then also we are getting the same output voltage. So this gives stability.
Okay, that sounds reasonable. Anybody with a difference of opinion? He's saying that this is a good circuit, or this circuit has a utility that the output stays fixed. And does anybody have a difference of opinion with that?
Sir, like I do know that the output should be stable, but
Hmm.
thinking about the operational amplifier should be the differential one. Then what's the fun of this if we are not getting the difference in the end?
No, you're not. So what? You're getting something. So you're right in the sense that it's not really looking like a very nice mathematical operation right now. But
Hmm.
that's a different thing. And if I make this circuit, as you have already said, several of you, that the output is going to be plus 12 volts as long as V plus is more than V minus. Okay. So the output is stable, it's fixed. So is that the reason why we want such a circuit, that you want a fixed output? Or can you see a fallacy there? There is actually a fallacy in that. Can you see the fallacy? There is something wrong with this demand. Okay, your statement that was made a while ago is as long as V plus is more than V minus, we are going to get plus 12 volts or plus VSAT. That's a fixed voltage. So we get an output which does not depend on the input. And we get a constant output voltage. So constant output voltage is the good thing about this. Do you see where the logical fallacy is there in this statement? I'm not even saying this is whether this is correct or wrong. I'm saying there's something logically fallacious about this statement.
But it will only be constant if
Yeah.
our V saturation and the minus V saturation would be fixed, I think.
Yeah, so you're right. But why is that a problem? Why is there a logical fallacy in this? You are in the right direction. It will only be fixed if plus VSAT is fixed, of course. But why is plus VSAT fixed? Where did this 12 volts or 11 volts come from?
So power supply.
Exactly. So if you have a very stable power supply, which does not fluctuate at all, then your VSAT will be fixed. But that essentially means that you will not need this. So to get a fixed output, you will not need the op amp at all. In order to get the fixed output, you would already need to have a stable power supply. And if you have that, why don't you just use a stable power supply? Why bother with using an op amp in between? You get my point. Plus
Yeah.
VSAT is fixed only if the power supply is stable. And if you already have a stable power supply, why would you need the op amp to produce a fixed supply? If getting a fixed output is the only thing that you wanted, you just use a good power supply. In case your power supply is bad and it fluctuates, then the VSAT will fluctuate also. So the op amp will not help that. So that is really not what the utility of this circuit. What is the utility of this circuit? In fact, some of you have already said what the utility is or what makes it useful, without perhaps realizing that you have said it. This particular circuit will produce plus VSAT always or not always. Will it always produce plus VSAT? Yes?
For the V difference to be negative, it would produce the negative V set.
Exactly. You're right. That has already been said before. But what is important is if Vn is more than 1 volt, that is, if I keep this fixed at 1 volt and change the voltage here and call this Vn, when Vn is more than 1 volt, you're going to get plus VSAT. When it's less than 1 volt, you're going to get minus VSAT. So what this does is that it compares Vn with this voltage and produces a big positive or a big negative output, which just tells you that is your voltage bigger than or smaller than 1 volt. It could be very bigger than 1 volt by a very tiny amount. Remember, for a gain of 10,000, that what that means is if V plus exceeds V minus by even a millivolt, even a fraction of it, 1/10, even 1 millivolt, then output will be 10 volts or almost saturated, right? So Vn can be very, very, very small amount more than more than V minus, and you're going to get plus VSAT. If it's very, very small amount less than V minus, you're going to get minus VSAT. So what this circuit actually is what is called a comparator. It compares. It allows you to compare the input voltage with the fixed voltage and produces an output which tells you whether the input voltage is bigger or smaller than the input one. And that has lots of uses. Basically, even in mathematics, wherever you have a comparison to make, an inequality test, you could test it using something like the comparator. Okay. So this is okay. This is not a linear circuit in the sense that the output is not proportional to the input. 2 volts output plus 12, 4 volts output still plus 12. Minus 2 volts output minus 12. Okay, but that's even forget minus 2 volts, 0.9 volts output minus 12. Okay, so this is not a linear behavior at all. If you were to graph V out versus V in, you will get something which looks like this. Whenever V in is more than 1 volt, it jumps to plus 12. Whenever V in is less than 1 volt, it falls to minus 12. And it's almost vertical here. It's actually not vertical. Close to this 1 volt, there's a very narrow region where you have a slope. The slope is so huge because of this gain being so big. It's a nearly vertical line. So this is the kind of V out versus V in that you get. Okay. So not a linear circuit, not one in which the output is proportional to the input, but a pretty useful circuit nonetheless. So even without any components, you just the op-amp, op-amp and the power supply, of course, you can actually create quite a useful circuit. And you will see in the lectures, in the video so far, that I will give you, I've already sent 2, but there will be more on op-amps. You will see that many very interesting circuits can be made with op-amps. And analyzing those circuits are very, very easy, simply because of these properties. This huge gain, huge input impedance, small output impedance makes analyzing op-amp circuits very, very easy. You can do them usually in your head. You don't even need to write much things down. Okay, so you will get your problem sheet tomorrow. Okay, and the problem sheet will have a small number of questions, but then there will be other problem sheets which you don't have to submit, perhaps. I won't mind if you submit it. It's just that you don't have to, which will have additional questions. So maybe by the weekend. And Monday we will start with JFET circuits, and then we will, for the other half of the class, we will answer questions or take queries about op-amps. Okay, so bye for today. We have a recording.